Alright, now that we've established our variables for angular motion, we're going to talk about our first concept. I guess we already did kind of talk about kinematics in simple terms when we talked about kinematics. We just talked about how to describe the motion. So we describe x as theta, so delta x is going to be the analogous to delta theta, and v is analogous to omega. So here v equals delta x over delta t, omega equals delta theta over delta t. Acceleration is change in velocity over time. Here, alpha, angular acceleration, is equal to the change in angular velocity over the change in time. And we have the relationship between each of these. X equals r theta, v equals r omega, and a equals alpha r. And then we also established that total acceleration is going to be made up of the tangential acceleration and the radial acceleration. And the relationship there is this is r alpha, this is omega squared times r. So we have talked about how to describe motion, displacement, velocity, acceleration for rotational values. But now we're going to talk about the other part of kinematics. Remember when we talked about kinematics for objects that are accelerating, we established that uniform acceleration is how we're going to describe all kinematics. Well, here, constant angular acceleration is what we're going to look at, and constant angular acceleration is basically the analog to uniform accelerated motion for linear motion. So what uniform accelerated motion describes for linear motion, constant angular acceleration describes for rotational motion. So I'm going to give you a set of 5 equations that are exactly matching the 5 kinematic equations that we learned all the way back when we did kinematics. And I wrote these equations in a particular way. Here I said we're going to consider x naught the initial position. We're going to set it on our axis to 0. And so we're going to do the same for our angular displacement. We're going to say the initial angular displacement is 0. And that does simplify the equations. How you see them on the AP sheet includes your x naught and your theta naught. Here we've just eliminated them. We've set them equal to 0, so they're removed from the equations. But you're going to see for linear motion, you've got v equals v naught plus at, x equals v naught t plus 1/2 at squared, v squared equals v naught squared plus 2ax, and the average velocity is given as the sum of the two velocities divided by 2. There is the exact same analog for angular motion. We can use kinematic equations for rotational motion, where omega equals omega naught plus alpha t, theta equals omega naught t plus 1/2 alpha t squared, omega squared equals omega naught squared plus 2 alpha theta, and average omega is the sum average of the two velocities. So when can we use these? We can use these anytime. We can use these anytime acceleration is constant. A quick connection to force means that we can use those anytime there is a constant force causing a constant acceleration. These equations will give us true values. So likewise, we can use these equations anytime our rotational acceleration equals constant. And so they're really just going to give us an absolute easy way to analyze changes in motion and changes in displacement and changes in position and changes in angular rotational velocities, and we're going to be able to solve them pretty straightforward, exactly like we learned to solve for kinematic equations. So let's take a look at just how easy this can be. We're going to take a look at centrifuge acceleration. And so if you don't know what a centrifuge is an object where you place these small and in a test tube, you could put a solution, and it could be mixed with a whole bunch of different things. And then that solution gets rotated around at such a high speed that it causes an acceleration toward the center of the circle that causes the materials to be separated by properties, and so they're density separated. So let's take a look at a centrifuge acceleration. A centrifuge rotor is accelerated from rest to 20,000 RPM, and that occurs in 30 seconds. And so what we're going to do is we're going to take a look at the average angular acceleration, and then we're also going to be taking a look at how many revolutions has the centrifuge rotor turned during its acceleration period. If we assume that acceleration is constant, so that means that we're going to find the overall displacement. So, average angular acceleration is given by the change in velocity over time. And here we've got revolutions per minute, which could be could be turned into a frequency if we turn it into revolutions per second. So 20,000 revolutions per minute can get changed into frequency. And so what we're going to do, I've misplaced my calculator, sad day, is we're just going to take our 20,000 and we're going to divide it by 60, and then we get 333.3 hertz, or 333 revolutions per second. Now we need to turn that into radians per second, and we know that 1 revolution is 2 pi radians. So that means that 20,000 revolutions per minute, or 333 revolutions per second, is actually 2,100 radians per second. And that right there is a velocity. So in order to use our kinematic equations for rotational motion, we need to consider what velocity is that. Well, it was accelerated from rest. Rest is clearly an initial velocity of 0 to 20,000 revolutions per minute, and so that's definitely your final velocity, and that occurred in a time of 30 seconds. So we can use W equals W naught plus AT to solve for, alpha t, to solve for our acceleration. So our acceleration is going to equal W over t, or 2100 radians per second divided by 30 seconds. So that gives us 70 radians per second squared. So now we've got our rotational acceleration, 70 radians per second squared. And now we want to know how many revolutions it's made. So what we're going to do is we're going to determine, we know acceleration, we know initial and final velocity, we know time. We do not, however, know displacement. So we're going to use a kinematic equation that allows us to solve for displacement, and we're going to use W naught t plus 1/2 alpha t squared. And we could use another equation. We could also use an equation that includes the final velocity, but this one's nice and simple, so let's go ahead and use it. That's a 0 value, and then this is going to be 1/2 70 radians per second squared times 30 seconds squared. And if we go ahead and solve that, we're going to get 3.15 times 10 to the 4th radians. So what's going to happen here is that if the displacement is 3.15 times 10 to the 4th radians, that's how many revolutions, or that's how many radians it's traveled in the 30 seconds that it was able to accelerate. And so what we want to do now is we want to determine how many revolutions, and we're going to use the relationship between radians and revolutions. 3.15 times 10 to the 4th radians. And it's 2 pi radians for every 1 revolution. So that gives us 5 times 10 to the 3rd revolutions, or it in that time revolves around 5,000 times, 5,000 revolutions in the 30 seconds that it accelerates. If we wanted to check our work, we could use another kinematic equation, and we would end up getting the exact same value. So you can see that this is really an example of doing a straightforward replacement now. Instead of looking at our linear quantities, if we're looking at rotational motion or how an object is rotating, then all we have to do is use our rotational values in place of our linear values, and we're going to get all of the data that we need. So what comes next is the relationship between how to use all rotational values to figure out linear displacement of a center of an object, which is going to come in our next lecture.